Good morning, everyone. Hello, and thank you for joining us today for session 2 of the Virtual Agronomy Expert Series. It's great to be back. It's great to connect with you again. Today we're talking everything nitrogen, a topic that we visited in the first series of Virtual Agronomy in session 3 specifically, where we discussed the different approaches and considerations to derive a nitrogen recommendation and to understand the nitrogen status in your soil and how technology and the new data and the sensors could all contribute to better estimating the nitrogen status and providing nitrogen recommendation. So please feel free to check the recording on our YouTube channel if you'd like to revisit that material. And at the end of the webinar, we concluded that experts may argue about the details of how to derive a nitrogen recommendation, but they all agree on two things. The very first one is that it's pretty darn complicated to account for all of the variables when it comes to nitrogen and understanding that cycle, as well as it's one of the very few important players in the life of the crop that we have control over. And so it's kind of our safety net to make sure that we are able to understand what the crop needs and to provide it at the right place, in the right time, at the right location. Thank you for joining us today and on such a very complex topic as nitrogen. It was a no-brainer to invite to the webinar two experts that have been working on nitrogen recommendation for more than a decade to discuss this topic with them. So I'd like to welcome Dr. Sotirios. Dr. Sotirios is an associate professor of integrated cropping system at Iowa State. Thank you for joining us, Sotirios, and Dr. Brian. Dr. Brian is a professor of precision nutrition management at Oklahoma State University. Thank you guys for joining us today and for sharing your expertise and work with us and our participants. We're very excited to dig deeper into your work, how the different environments and crops that you're working with, how does that influence the nitrogen approach that you've adopted, and learn more about your contribution to the nitrogen body of knowledge and all the research that you're part of. So again, it's a pleasure to have you on board and thanks for joining us today. So let's start with today's session's outline. The agenda today is we're going to talk about data modeling and remote sensing, how it can all enable nitrogen recommendation and how it all plays together to create a dynamic loop of understanding the nitrogen cycle. Then we're going to talk with Dr. Brian about the nitrogen-rich strip and the sensor base recommendation. And with Dr. Sotirios, we're going to cover the cropping system modeling. We'd like to understand and talk with our panelists about the challenges of each of these approaches, how do they satisfy growers' need, how does adoption around them, and we want to discuss the advantages and the limitations. And what does the future look like in those different methodologies? So I'll start talking a little bit about modeling and remote sensing, how combined we are able to understand the status of the crop, which is quite fundamental to give any nitrogen insight on what's going on. So starting with the basics of the basics data sets, which is understanding the weather, the planting date, the planting density, and understanding your soil. All of these combined will give you the condition of your crop. It's static, so it's at one certain point of time. This was the weather, this was the planting practice, this was the date, and this is the soil situation. And from that, we are able to understand the conditions of the nitrogen, how much the plant needs and how much is available in the soil. What we want to unlock and what the capability of using remote sensing is creating more of this dynamic aspect of taking that data, running it through an agricultural model in order to provide a recommendation. And in that way, we're not only looking at the data sets at one specific point, we're more looking at throughout the season. And we're trying to understand what is the potential and how we can drive our crops to achieve the maximum yield that we want to shoot for. So when those basic data points enter into an agricultural model, you're able also to rely on the remote sensing data that is collected either by imagery from satellite drones or handheld devices that Brian is going to talk to us about. All of that combined also feeds into the agricultural models to predict the nitrogen condition and situation throughout the growing season. You see there's this yellow icon of the grower. The grower is a big part of this decision loop of deciding when is the best time to apply the nitrogen, how it makes sense to his practice, to his machinery. But all of this combined create this dynamic loop of you're calibrating your models, you're using data points that gives you an overview of your whole field, not only your field, your county, and the average of your state, all to feed into understanding what is the proper recommendation, what is the proper amount of nitrogen that your plant will need. With that combination, I want to start with Dr. Brian to begin with. You use different data points and you combine them together to provide a nitrogen recommendation using the enriched strip approach. So let's start with like the where, the what, the how does it work, and talk about the grower's experience when adopting this approach.
Hello, everyone. My name is Brian Arnall. I'm with Oklahoma State University. Been with OSU since 2008 as a faculty member. My current role is a three-way appointment. At land grant, we have the extension, teaching, and research legs. And so I have a three-way appointment in which that I serve extension as my primary role, teaching is my secondary role, and research is my tertiary. So my split is actually 55, 35, 15, and that covers what I do with OSU. My background is in optical sensors and nitrogen management. I had early role as a graduate student in the development of the Green Seeker sensor, which is an active NDVI sensor. So we were able to, I had an opportunity to work on that before it was commercially available and see how it went. Today, I'll kind of go through the hows of how we utilize an active sensor in the Southern Great Plains throughout Oklahoma, Texas, Kansas, and how it's expanded on beyond that. We'll go through some of the theoretical aspects of the system, and then how it's applied. As an extension specialist, I have a lot of hands-on experience with this technology, both good and bad, and so we've been able to break it and find a lot of success stories through it, and I'll go through that when we go through my presentation. The application of what we do with the Green Seeker comes from two-part. We really go back to the Stanford equation when it comes in looking at an approach to nitrogen. We look at it in fertility, the traditional Stanford equation, which is that crop nitrogen minus soil divided by the efficiency factor. What we're really trying to look at is a soil test. If you look at the old yield goal soil test recommendations, it goes back to yield goal gives you the crop, soil test gives you a soil, and there's an efficiency factor on the backside. In corn, it was 1.2 pounds of N per bushel. In wheat, it was 2 pounds of N per bushel. That's not what either crop actually has in the crop. That's the fudge factor that the efficiency adds in. So corn is, maybe 0.8 pounds of N per bushel in the crop. The 1.2 is an added efficiency factor. So you get the crop and the soil in that. For us, we're looking at it, we can go back, and at Oklahoma, we have the blessings of have a lot of long-term fertility trials. So the one graph that you see right there is from a study that we're cutting the 50th year of harvest from. It has NPK plus, and we have 3 or 4 of those. We actually have 5 of them across the state that have more than 50 years of nitrogen, phosphorus, potassium applications. And we have others that have over 30 years of data on it, so we can really look back and look at the impact. The point of this graph was the orange bars was the maximum yield achieved in those years, and this is in bushels, so I apologize for not being in metric, but it is in bushels of winter wheat per acre. And so you see the range of this location goes truly from about 30 bushel or 2 ton up to nearly 80 bushel, getting closer to the 3 and 4 ton realm over the span of 2004-2019. So highly variable yields over that time frame. We average somewhere around 4 ton. This location is a 4 ton average. And then the black bar is the economic optimum N rate in that given year, because we have a nice nitrogen rate trial here. So you can look at the optimum range. Even if you look at 2014 through 2019, the economic optimum nitrogen rate runs between 20 and 100 pounds or 120 kilo per hectare of nitrogen. So in a 5-year time frame, our EONR has 120 kg range, or 112 kg range in a 5-year span. So the challenge for us is really, how do we know how to determine nitrogen rate? It is related to yield because our crop, it is related to soil because of the amount of soil that is released. Because if you look at our EONR, it's not correlated to yield. If you look over the 20-year time frame for multiple long-term studies or on-site studies, optimum nitrogen rate has zero correlation with yield. It has trends with yield because the amount of nitrogen in the crop is related to how much we need. However, the soil contribution has such a drive in that too. Our soils have about 1.5 to 3% organic matter, but because of our variable weather, we can either have a net immobilization season, a net neutral season, or a net mineralization season, and we can easily have a 40 to 50 kilo swing in net immobilization and net mineralization from one season to the next, just depending upon rainfall. And so our weather patterns being so diverse is really challenging to predict what we're going to have. So what was developed, and I'll get to a timeline later, but the approach that's been developed in Oklahoma was that we look at a parameter of an active sensor reading. NDVI is our case, is what we ended up on. A time frame, so NDVI and a time frame, we use growing degree days greater than 0. How many days is that crop grown? And then expand out. The expansion comes from the use of a strip. It's critical for us that we put out a nitrogen reference strip in the field that has unlimited. We usually have anywhere between 20 or 40 to 70 kilo per hectare extra nitrogen in that strip above the farmer practice. And we look at the difference of the two. And what we use is the growing degree days and NDVI to give us a biomass produced per day. And this biomass produced per day gives us a good estimate of final potential grain yield if everything stays the same. And we're predicting a potential yield, not an absolute yield, because we don't know if the weather gets better or if the weather gets worse or pest. So we predict out a potential yield. And in short, what I tell my farmers that I work with is that if the nitrogen-rich strip has a yield potential of 4 ton, but the unfertilized farmer practice or the less fertilized farmer practice has a yield potential of 2 ton, in the end, we may need to make up that difference, because the 2 ton potential of farmer practice is saying that's what the environment is providing, and that's what your pre-plants are providing, and this is where the crop can get. So we need to make up that difference between the 2 ton and 4 ton with fertilizer. And so if you want to go ahead and click forward one, pardon me, we use this responsiveness and the predicted measure at the time of fertilization to get our top dress rate. And we've primarily developed this off of we're currently using as a flat rate. OSU uses a flat rate, so a field rate. Manuel, can you click forward one, please? When we look at this as a variable rate application, which was actually first developed, the on the go, so this is if you uploaded it into an applicator file, as it goes to the field, takes points to the field of NDVI. This is how the nitrogen application for the Great Plains would work, is where if, pardon me, if the field looks as good as the enriched strip, we don't apply fertilizer because we say it has enough fertilizer to make final yield. Up to a point, we're increasing nitrogen rate up to a point as NDVI lessens below the enriched strip. But specifically in Oklahoma and the Great Plains, we know there's areas of the field that will not catch up. Poor stand, maybe it's a drowned out area, things like that. And so we actually start pulling back. So you look at the lower level of NDVI, we have some nitrogen because it needs some. We go up to a peak right there on this example of 0.6 as the maximum rate, then we draw back down. Places like Virginia Tech and in Mexico, when we've done this work in irrigated situations, the curve looks different. So we actually change this nitrogen application curve based on the environment and the soils. down in Mexico when we worked in Ciudad Obregón with cement, the in rate went up and then plateaued because it didn't matter inversely. It didn't matter how bad the wheat looked in Obregón, we could catch up. All you had to do is pour the nitrogen to it and it would make 610 yield. It didn't really matter when. And so you peaked up and then you came down. Inverse, in the sandy soils in Virginia, where they have deep leaching, the really good corn and wheat received more nitrogen. And as it went poor, it went down because effectively you had to keep that good corn in good condition because it was highly leaching. And so what we've worked on over the years is these models are very dependent upon the soil and the mechanisms. And so we don't have one nitrogen model that fits all. We have a nitrogen model for each scenario. It might be even in dry land in Virginia, has a different model than the irrigated sands on the eastern shore in Virginia. So that's one thing we've learned over the years is there's not one model that fits everybody. It is truly an environmentally based nitrogen response model and how we hit the agronomics by the needs. If you advance one, I like to put that, you know, this machine down in the bottom corner, well, I'll start first. So the first work at OSU developed was in 1993 using passive sensors to collect the data. And so it is fun. The first work they did actually had inverse relationship where they used the sensor and the yield response because the tractors and the lawnmowers to carry the equipment of the sensors and the batteries and the desktop computers, because they had desktop computers hooked up to a generator carried by a lawnmower with platforms to carry the passive sensors, it inversely affected the soil. And so we went back all the way to the old work in 93 first work. The same time the reference strips were developed or discussed, first proposed in the early 90s. That machine down the bottom, we had it on it was a 20-meter boom with the sensor about every 20 inches. So not getting that conversion quickly, but the sensor was over every nozzle bank. That was available in 2003 and we field tested it. And you had an accuracy of changing nitrogen rate plus or minus about 7 kilograms of N per hectare at a sub-meter resolution. It was about a 0.6 meter by 0.6 meter was the resolution we were applying in 2003, and was doing quite well. The problem was the cost was so high. So it's been funny that we had the science and the technology in 2003 to do it, but we've been working backwards to get something that's more scalable and easier for the producers to use. So we go to the middle picture. That was the handheld sensor that we collected all the data with in the early 2000s. It cost us $4,000 at the time, and it was primarily the data collection. The heads on that sensor were the same that's on the on-the-go sprayer. And then in 2012, we kind of took it down to the handheld, much less smart, but much cheaper, and that was a retail value of $500. So it's funny that in 2003, we had the science and the technology, and we've actually been going backwards in the resolution of technology to apply the science. And so we're getting a coarser and coarser to make it economically viable. In 2003, OSU did its first efforts to put out enriched strips in farmers' fields, and there was 62 fields that a master's student applied in that time. By 2011, there was about 500,000 acres of strips throughout Oklahoma and Kansas that was not applied with no help at OSU. In the last check we have about 1 million acres throughout the Great Plains utilizing the enriched strip. This was even in 2003 that we put the sensor on a high clearance sprayer, and those sensors were applying by row every 0.3 meter, changing rate every 0.3 meter of row. The goal was to actually apply every corn plant in a dryland situation in Oklahoma. So it's not like the Iowa states where we have 35,000 or 40,000 plants. This was about 16,000 plants. So we were able to get to almost 1/3 of a meter resolution with those sensors moving at a slower. In the applicator, we were moving on larger fields. It was more of a 0.5 meter of row, making that fertilizer change. So it was anywhere between 3 and 5 corn plants that were making that change. Again, that was in 2003. And it worked well for us then. It's that transition on. So if you can click one more. I like this picture because this was our advanced version of the early sensors before we had an active sensor. it took about 3 graduate students to collect the data off these wheat plots, because you had to have one hold the laptop, one hold the sensor, and the iteration before this, you had to have one carrying the battery pack. And so things have progressed greatly. Now we get into this and in our application of it. I love this. This is a Google image that I pull on the right-hand side of farmer fields. I can now go in Oklahoma and Kansas and find enriched strips from farmer fields because Google's updating regularly. And this is just how it's used. The fun aspect of this in the winter wheat crop is how it's actually moved. So when we started this, farmers put all their nitrogen up front, anhydrous ammonia applied pre-plant 30 days before planting. This has given them the confidence to move in season, and now we see an absolute move where they do not put on any pre-plant nitrogen other than what's banded in furrow with the seed. So they're getting anywhere between 8 and 12 kilo of nitrogen, and they're delaying the fertility management until they know they have a crop, a stand, and a growth, and they're saving significant monies. So we've gone from, in 15 years ago, farmers were averaging, they applied 2 pounds of N per bushel produced, and they actually harvested about 2.5. Now our producers that are utilizing the enriched strip on a flat rate basis, one rate across the field, they're now at about 1.5 pounds of nitrogen per bushel. And they're delaying it. And so the delaying of nitrogen is actually producing better protein. So they're getting more yield for less nitrogen and a better quality, in quality, both baking, milling, and protein quality on our winter wheats and spring wheats as we move into the Pacific Northwest. And this is some data from Kansas showing that we have a great time frame where we have very little nitrogen accumulation and we can apply it later in the wheat and greatly recover. If we want to click forward one more. Our grower experience. This is just stuff. Our feedback over, I've been working with the enriched strip since 2003. So it's getting on several years now. The one thing is it takes too much time. I don't want to deal with it. I don't want to wait on it. That is the one thing we always hear about the enriched strip. And I honestly tell farmers, I don't care about the sensor. I want the enriched strip because it tells me if I need more. Even if you think you have enough, it'll tell you. But it's allowed our producers to move away from pre-plant because they have confidence in that enriched strip to make in-season more accurate estimates. Here's what we say, and this is some experiences. So one farmer spent 10 hours applying over 2,000 acres of wheat and roughly made about $42,000 return on investment. So it saved him about $4,000 per hour invested. Northeast Oklahoma, the producer up there. And so this is 3 very different environments. All of them are averaging between $2,000 and $4,000 of hour invested to put out enriched strips and sense them. This is on a flat rate. This isn't even variable rate. And we say, well, what about the change of zones across fields? We have multiple soil types across the field. How do we deal with that? My first question is to the farmer or the producer or the agronomist, are you already doing variable rate nitrogen? If the answer is no, then I say you're already ignoring those zones. So let's improve your average rate across the field. Then if we go into that and then we start doing zones, zones can be by soil type, it could be by yield. It depends on the region. And so we have a lot of producers that do strips by zones, high, medium, low yield, or coarse to fine texture zones. And we do those based upon what makes agronomic sense of that location. We found that in our winter wheats and white wheats and spring wheats, moving from pre-plant to in-season and using a recommendation like an enriched strip is getting much better standability. We don't have the lodging in those crops that we do when we have pre-plant nitrogen. It's always, well, I don't have time to do it. Then what about the in-season? It gets too short for us. And the funny thing is that once they try one field and that field works, they go from it's impossible for me to sense and apply and manage this ground to it made me so much money. Now I've been doing it for 15 years and I can't not do it. And so it's a learning process that once you learn the value in it, you learn how to make your system adaptive and adaptive to it. And we're also learning we have a lot wider time window to make applications in all of our crops than we first thought. Our winter wheat crop has a huge application window to maximize profitability. Our corn window is growing, and our capability to do in-season corn management is exceptionally growing. Especially in our area, we have more and more pivots with fertigation. And so we're really utilizing this with fertigation. My last point on the corn side, as we move with corn, I cannot get a corn farmer not to put on 180 kilo to 300 kilo in some cases per hectare pre-plant. So what we've done to still allow them to put on pre-plant and manage that is have 0 end blocks. And this was first developed by Virginia Tech, where they use 0 end blocks, and kind of look at it backwards. It's still the same approach, but the 0 end block is telling us how much can that environment provide, and when is the environment actually running out of nitrogen for the crop, and when does your fertility take over. And those 0 end blocks have been really successful with getting the irrigated corn into a reference technology. My last real comment comes in with that our goal, my goal as an extension teaching and researcher is to be site specific. Site specific needs site specific data. It's really hard to do correlation calibration curves on every single field we have. So one thing we can do is have test blocks of nutrients out there, whether that's NPK or even lime, and find out how does that crop in that soil type, in that environment respond to this nutrient, because we know it's different. Unfortunately, we use averages. And so we're trying to do site-specific information with an average data set. We need site-specific information, or we do site-specific application with average data sets. We need site-specific information to feed into whether it's this or the models that Sotirios is going to talk about. That site-specific data, however we gather it, makes our system so much more accurate, and we can truly do site-specific applications.
Indeed, and being site-specific implies also knowing about the environment, knowing about the soil, as you very, very well spoke to. And Sotirios, you're more focused and you're more thinking on where's the source of water? How's my irrigation? How does that relate to my nitrogen recognition and to my approach to giving nitrogen?
I can't hear you. I'm sorry.
Okay. So Sotirios, to you.
Okay. Can you hear me?
Yes.
Okay, good. Hello, everyone. Sotirios Archontoulis. I'm associate professor in the Department of Agronomy, Iowa State University, and I have research and extension responsibilities. My research is to improve the efficiency of corn and soybean based systems, and by identifying a combination of practices that improve yields, profits, and at the same time we decrease the nitrogen loss from the system. My extension focus is to disseminate information from models or experimental data to stakeholders via decision support tools. In my lab, we are using simulation modeling and APSIM in particular to help us address this complex problem. And we also collect experimental data to verify and further improve the model. In the next 3-4 slides, I will give you some highlights of the research. And I will start with describing the environment. It's a little bit different from the one that Brian talked. We move a little bit north to the Corn Belt. And this map shows the distribution of the cropland. And basically, you can see only 2 colors there. One is yellow and the other one is green. And if I translate the colors to names, it's corn and soybean, the majority of the crops we have there. We don't have much diversity. The environment is quite variable there. For attendees that are outside US, for reference, I want to mention that corn yields are about 10 to 12 megagrams per hectare on average, can be much higher as well. And soybean yields about 3 to 4 megagrams per hectare. And 90% of the area is rain-fed. There is some irrigation in Nebraska, Kansas, and some other parts, but the majority of the area in the Corn Belt is rain-fed crop production. Nitrogen fertilizer, it's a big issue. I would say a topic of research since the introduction of fertilizers. We try to keep come up with better equations, better tools. We don't have yet the perfect tool, but we are trying. On the challenges, to me, the main challenges with nitrogen recommendation in this environment are 5. I'll put there some bullet points. The first one is the time of prediction. Farmers start applying nitrogen to the cornfields 4 or 5 months before planting. Of course, the maturity goes around planting, couple of weeks before planting, and a little going during the season. So predicting the optimum nitrogen months before planting is extremely challenging. The second challenge is the too many factors involved in the optimum nitrogen rate. Brian showed the equation there, but if we split the equation into all the factors, probably we need 2 pages, 2 slides to put all the factors there. There are so many. And in the same time, we have too little data, basically weather and some static soil information. We need more data and different data to come up with some more accurate predictions. Another challenge we have in the Midwest is the rain-fed crop production. Precipitation is uncontrollable. The farmer can apply nitrogen and the day after or 2 days after get 2 inches of rain and lose a big portion of nitrogen. In irrigated areas where portion of the water can be controlled, the challenge, the weather challenge is less in my opinion. Another challenge we have in the Corn Belt is that about 50% of the soils have a shallow water table. So this is an important factor because influences all the soil processes, denitrification, leaching, mineralization, everything. In the same time, it affects the crop roots and how much nitrogen and water the plant can take up, and then we go all the way to yield. So it's important determinant of crop production in the Midwest, but very difficult to predict and highly dynamic. Within a season, the water table can be from 30 centimeters all the way to 3 meters, depending on evapotranspiration and many other factors. On the methods that are used in the Corn Belt, there are many, but and I have there a list. But what I want to mention is the survey that I read a couple of years ago, that farmers, they are not using just one method. On average, they use at least 2 methods, perhaps the yield goal and some soil nitrogen test or the MRTN approach. They use multiple approaches. Now in the next slides, what I'm gonna do is I'm gonna share with you some lessons we learned from applying simulation models to predict the yields and the optimum nitrogen rate. So if we can go to the next slide, please. Thank you. Since 2015, we used APSIM to forecast corn and soybean yields and soil nitrate and soil water every week at 10 different Iowa State University research and demonstration farms, which are distributed across the state of Iowa. In the same time, we collected all possible measurements, soil, crop, roots, to check and improve the model accuracy. And the 2 graphs that I have on the left, the top is about the nitrate and the bottom one is about the yield. This is basically the prediction protocol and how we make predictions at planting and then every week after planting. Basically, what we did was to use the weather up to today, and after that to use a synthesis of historical weather years so we can come up with a probabilistic estimate of expected nitrate in the next week or expected yield at the end of the season. All this information was publicly available through an extension website, and we were updating information every week. And important, we displayed in the website both simulated and measured data because we want to show to the growers what's the accuracy of the tools and simulation models. This is kind of the transition to the digital agriculture that we talk. The results from this study are published in Crop Science a couple of months ago, but what I want to focus in the next couple of minutes is about the lessons we learned by forecasting yields and nitrogen, soil nitrate over the last 4 or 5 years. If you can please advance it to the next one. Thank you. Okay, the lessons. What we learn from doing all this work. The first one is the importance of the water table. As mentioned before, in this environment, it can vary from 30 centimeters to 300 centimeters, depending on the number of factors, and has lots of influence on yield, roots, water supply to the crops, everything. In some of the years, the water table provided a yield credit and also credit in nitrogen supply through enhancing the soil nitrogen mineralization. And in some other years, provided the opposite, increase the nitrogen losses and inhibit the maximum rooting depth. And what we learn is that it is very important to account for this factor in the prediction protocols, no matter which model we're using. It's a big factor and affects the yields and the response to nitrogen. The second lesson was about the importance of the initial conditions and especially measurements of soil nitrate. We found that these measurements were very helpful for accurate predictions. But unfortunately, very few people measure this, and we believe this is something that altogether we should start taking differently when we develop future data collection protocols. We need to capture the system. This is what we don't have today. We have lots of data about yields and nothing else. Of interest was the importance of the management factor, of the management information, the accuracy of the management information. That was very important, and together with the initial conditions accounted for 1/4 of the corn yield variability, which is significant, and in my opinion should not be ignored. We typically blame the models when the precision is not good, prediction is not good, but 1/4 of this going back to the data that we use to make the predictions. So we need to be careful and to look about high quality data inputs or approaches to eliminate some of the data inputs. Another lesson is that getting the leaf area index and biomass production trajectories right early in the season was a key to have accurate predictions towards the end of the season. If the model doesn't make a good start, then there is nothing else you can do to make this, to make a correction. It's very important to have a very good start. And this is an area where I believe remote sensing can be of great help to get early season trajectories right. The model can pick it up from there. Next lesson was about the prediction time. That was a surprise to us. We were expecting yield prediction accuracy to go up as we move towards the season, but that was not the case. We found that the prediction at planting was the second most accurate after the prediction at harvest time, where we had all the weather. We explained this by the buffering capacity of the shallow water table. When you don't have enough water, the water table supply. When you have too much water, the water table brings a penalty, and somehow the yield is not very variable in this environment. In an environment without water table, the variance in yield can be 3 to 5 times larger than in our environment here. So this is how we explain this good prediction of planting. And overall, this is good news, because at planting or near planting time, there are lots of management decisions that take place. So it's good to have a good prediction there. The next lesson was about when do farmers need the models, the results from the models. We were disseminating the results every week, and we noticed that the traffic, the web visits, were 5 times more in June than the other months. And the reason is that, first reason is June probably is the last month where farmers can take actions and improve their management. And second one is that in June, in general, the corn prices are the highest. So farmers make decisions about crop yields and selling or all this kind of thing. So It's very important to have models that can provide information as early as possible. Also, through all this work that we did, is that prediction is one thing, but scenario analysis is another thing. And farmers really asked for this type of information. It's nice to learn what happened the last year so they can improve and study and design something better for the next year. The model, the APSIM model that we used, we checked several processes, we collected lots of data, and we were happy how it was able to handle all the system, a good balanced performance between crop and soil processes. I think all these lessons are relevant for many prediction tools, and predicting yield is very important for predicting nitrogen. And let me share you some results from another study. Can you please move to the next slide, please? Okay, what we did here with Dr. Laila Puntel, now is an assistant professor in the University of Nebraska. We used 15 years of experimental data with two crop rotations, corn following corn and corn following soybean. And we used APSIM to predict the economic optimum nitrogen rate. And I would like to define what is the economic optimum nitrogen rate and how we calculate this is very important. It's basically the point from the yield response curve where it reaches the maximum, near the plateau. And we like to do the simulation analysis here as a means to get all the many factors including through a simulation model. In the figure, in the diagram here, you can see that we have the inputs, which are the management, the environment, and the genotype. All these inputs affect soil and crop processes and the supply and demand, and then generates an emerged outcome, which is the yield response to nitrogen. And from this response curve, we get the optimum. Next, please. On the right, you can see the results of 15-year experimentation. These are the average data. X-axis the nitrogen rate, Y-axis the corn yield, and we have three lines there. One is the observed data, and the other two is about APSIM. One before doing any calibration, and the other one after calibration. And we were pretty excited about these results. And I put there two yellow stars to indicate the optimum range. And it did a good job. And this led us to the next research question. Next, please. Was, well, since we can simulate the data, can we use it as a forecasting system? And what we did there was we followed the same protocol I described previously, and we made predictions of planting, B6, R1, and then the last one was at R6. In this graph on the left portion, I show the yield prediction at planting and at R6. And we were very happy with the model prediction of the yields. When I say yields, it was yields at different nitrogen rates, the 0 all the way to 250 kilograms per hectare. Good performance, unbiased predictions, but when we computed the economic optimum nitrogen rate using the yield data, what we found was the results are not as impressive as the yields. Although they are not biased, but we cannot get super high predictions. And this is what this justifies the title that I put there, that predicting the optimum nitrogen rate is 5 times harder than predicting the yields. You really need to have the yields perfect in order to have the equal performance in the economic optimum nitrogen rate. A little up or down in the yields in the response curve can have a huge impact on the prediction. An encouraging point from this analysis was that around 62% of all the cases, the model predicted accurately the direction of the optimum nitrogen rate. is this going to be an above average year or a below average year? So we were happy with these predictions. Last slide. We are currently exploring different methods to improve predictability of the optimum nitrogen rate. One project that we are very excited is a recent collaboration with FluroSat, which we try to combine the power of APSIM model and remote sensing in the Corn Belt, and to predict the nitrogen at different zones within the field. I'm looking forward to the results of this project. And the second one, we explore alternative, easy to use methods to predict nitrogen rate at the regional scale. And
perfect.
I will
thank
stop
you.
here.
Thank you, Sotirios. Can you guys hear me? Perfect. I finally was able to figure out how to log in through the phone. Thank you guys very much for walking us and telling us about what you've been doing with nitrogen and your approach to that research and the recommendation. What you said, Sotirios, is something that we are also very excited at FluroSat to bring a heavy input model into a way where, one, we can emphasize how remote sensing could derive and could weigh in and be part of substituting those inputs instead of you figuring out what you planted last year or when did you harvest or what was the peak. We can get all that information from the remote sensing imagery. So we're really looking forward to our collaboration and to try to automate more inputs, because input has been an obstacle when it comes to reaching out to a farmer and saying, let's run this model, let's simulate, let's create a digital twin and give you a nitrogen recommendation. Sitting down, I found that to be quite problematic, sitting down, especially during the season, sitting down and asking him all these questions and putting all the inputs needed. So it is representative. There's no way you can go about that. So really excited about all the automation. We've done a lot of it, about 70% of APSIM, and really looking forward for the automation that we're going to be working with you and the people at Iowa State to move forward. Something I want to come back to that both of you guys touched on was the fact that, deciding on how much nitrogen to add, sometimes you don't have the luxury. You're limited by the weather. You have a small window where you need to make a decision. You need to decide how much to add and to go out there and put it. So my question, and I'll start by you, Brian, is could you tell us a little bit about when is the soonest, when is the earliest to go ahead and use the approach that you described, enriched, to come up with a nitrogen recommendation and a nitrogen number that you want to use?
So that's a great question. It's relative. So as you move further north in the Corn Belt, it becomes later and more challenging because the residual nitrogen organic matter. One of the things that we've moved through in the Great Plains and it's been quite successful, is the move away from pre-plant. So for the reference strip to work on the high side, all you need is there to be a nitrogen deficiency in the field. And that's what we're working off of, is when the strip becomes greener or have more biomass than the rest of the field. So that's nitrogen deficiency. So in areas of high residual nitrogen, it takes a little bit longer to develop out. But that's also why we've had to move away from pre-plant. On the flip side, in the corn, when we go to zero nitrogen, it's at the same point that we are waiting for the environment to run out of nitrogen. So how much residual nitrogen is there? Most of the stuff we worked with, if we go back to what has been developed at Oklahoma State, and why we've stuck with the NDVI instead of maybe the red edge, is to be earlier. And so we want smaller and smaller biomass. So in corn, ideally a lot of our work was in the V6 growth stage is when we want to start making those recommendations. We have a little bit of growth. But to get V6 response to an enriched strip, you cannot put down pre-plant. So this is this is a primarily in season. That's why you'd also be able to go with the zero and potentially use it that way. On winter wheat and spring wheats, it's anywhere around that jointing stage, whether you want to say the feek sticks or it's when you have that stem elongation prior to that. our winter wheat window is honestly from the month of January, even in December, up through late March throughout the Great Plains. So we have a really long window. In the spring wheats, it's about a 30 to 45-day window.
Thank you, Brian. So Sotirios, in the same light, and with what we're doing, with what we're talking with Brian about, which is, limitation of when can I get started to when can I get an answer. John is asking us, like, what are the early season trajectories that remote sensing can help with, especially when it comes to modeling?
Yeah, remote sensing can help a lot with determination of the leaf numbers or leaf area index. Knowing the phenology and get right the early phenology is extremely important. It's extremely important. So early in the season, in the first 3 weeks, if we get an accurate estimate there, I believe predictions from the model will be good. On the second part about predictability and when we can come up with a good estimate, and I agree with Brian, this is highly environmental dependent, and depends also on the soil hydrology. And I mentioned the example from Iowa, and poorly drained soils with a shallow water table, the yield is not very variable. But in well-drained soils with very high yields, you can also have very low yields. So prediction in those soils, it's trickier.
Yes, indeed. And like you said, like we can all think about the nitrogen and say early on, later in the season, but it's in those extreme environments that tools like that, you've got growers knocking on your door and reaching out to the extension units in their area and being like, it's so extreme, I don't know what to do, which we're having a lot of those years. So it's indeed all about everything related to get to everything related from the environment, whether to the soil, to the irrigation, to the water, available water, to come out with the nitrogen that would make sense for that application. We're a little bit over time, but I wanted to thank you for joining us today and to thank everybody who was on the call. We wanted to share with everybody on nitrogen specifically the different approaches, but we all agree on the complexity, and we all agree that it is one of the very few inputs that we have control of. There's no guarantee it's going to rain. There's no guarantee the pricing of whatever commodity we're planting is going to be satisfying come the end of the season. But nitrogen is one of those few things we have control of, and it's your safety net. So definitely that puts it in the light of how important it is. Again, thank you very much for joining us today. Thank you for sharing your experience. Pleasure having you guys on board. Thank you everybody who attended the webinar.